So with just this formula, it is basically enough to solve most problems that you'll see regarding the divisor counting function. So let's start with this Amy problem. So we wish to count the number of divisors of this integer that have exactly 2004 divisors themselves. So how should we start with approaching this problem? Yep, since the divisor counting formula requires the prime factorization, it would be a good idea to find the prime factorization of the numbers involved. So 2004 to the 2004 is this large number, because 2004 is 2 squared times 3 times 167. Now we wish to count the number of divisors of this thing that have exactly 2004 positive divisors themselves. So how will we do that? How will we find out which divisors have exactly 2004 divisors? Well, yes, we essentially prime factorize 2004 here. We just have another power of 2004 in the exponent. So if we take an arbitrary divisor of this large number, then it has to be the product of 2, 3, and 167. It can't have any other primes in its factorization. And the exponent of each of the primes has to be at most the exponent of each of the primes in the corresponding factorization for 2004 to the 2004. So we can represent each divisor of 2004 as 2 to the b via a times 3 to the b times 167 to the c. Does anyone have any questions so far? Well, with this basic setup, we can now say that this divisor has a plus 1 times b plus 1 times c plus 1 divisors. And so we need a plus 1 times b plus 1 times c plus 1 to be 2004 per the problem conditions. But we also have these size restrictions on a, b, and c. They can't be too large, otherwise they won't be divisors. But we can actually ignore this because this automatically implies that a, b, and c can't be more than 2004. Each of the factors is at least 1, since a, b, and c are non-negative. But if any of a, b, and c is larger than 2004, then its factor is at least 2005. And so the inequality can't hold. A plus 1 times b plus 1 times c plus 1 will automatically be larger than 2005. No, 2004. So we just want to find the number of non-negative a, b, c, such that a plus 1 times b plus 1 times c plus 1 is 2004. How might we approach this? Well, in this case, taking the prime factorization of 2004 is useful. So we'll now have to consider cases. So there's one factor of 167 on the right-hand side. That means one of the 3 factors on the left-hand side has to be divisible by 167. So there's 3 ways to assign which one of a plus 1, b plus 1, and c plus 1 is 167. Does anyone have any questions on why this is the case? We're basically considering the prime factorizations of a plus 1, b plus 1, and c plus 1. And one of these prime factorizations is going to have one factor of 167. And there are 3 ways to do that. Similarly, there's 3 ways we can assign the factor of 3. But now we have 2 factors of 2. There's a 2 squared on the right-hand side. So how many ways are there to assign the factor of 2? Yep, there are 6 ways. Well, you can consider a couple of cases here. If both of these factors of 2 go to the same variable, there are 3 ways to pick which variable they go to. And if the 2 factors go to different variables, there's 3 ways as well in that case. So adding them up, you get 6 ways to assign the factors of 2. Now these cases are independent. So how we assign the factors of 2 doesn't affect how we assign the factor of 3. And so we can just multiply to find the total number of ways we can pick A, B, and C. So 3 times 3 times 6 is 54. Does anyone have any questions about this? If not, then we can move on to our next problem, which is also about the divisor counting function. And I'll give you a little bit of time to read this. And if you have any ideas, feel free to type in the chat. So to begin, we want to find when we have a sum of taus, and we want to know when it's even and when it's odd. So you might already know exactly when tau of n is odd. As you've mentioned, it happens when n is a perfect square. And if you haven't seen this result before, we can prove it with the divisor counting function, the formula. So if we assume that the exponents in the prime function are e1 through ek, then tau is e1 plus 1 through ek plus 1. And this tau of n is odd if and only if all of the factors are odd. If a single one of the factors is even, then tau of n will be even. And assuming that all ei plus 1 are odd, that means that all ei are even. And if all of the exponents in the prime factorization of n are even, then n is a perfect square, and vice versa. So this way we know that tau is odd if and only if n is a square. So we're not exactly concerned with tau, but we're concerned with the sum of taus, tau of 1 through tau of n. So we can see that s of 1, s of 2, and s of 3 are odd, because tau 1 is odd, but tau 2 and tau 3 are even. So tau 1 is odd, tau 1 plus tau 2 is odd, and tau 1 plus tau 2 plus tau 3 is odd. But when we get to tau 4, that's also odd. And so s is going to switch sign. S of 4 through s of 8 are all even, because tau 1 and tau 4 are odd, and every other tau up to 8 is even. And next, s of 9 through s of 15 are odd, because there's tau 1, tau 4, and tau 9, but no other squares. And we can continue this pattern. So since perfect squares are so essential in determining when S is odd or even, we want to consider the parity of S from 1 to 2005. It's a good idea to try to find the squares that are around 2005. And to spare some calculation, 2005 is between 44 squared and 45 squared. And 44 squared is 1936. So now, from the pattern above, we can extend our logic to determine exactly when S is odd. So under what conditions is S of n odd? Well, S of n is odd when there are an odd number of squares that are up to, yep. So to be precise, we have n from 1 squared to 2 squared minus 1, because the only square under these values of n will be 1 squared. Then 3 squared to 4 squared minus 1. The squares less than this are less than up to these are going to be 1 squared, 2 squared, and 3 squared. And so on. And up to 2005, it goes up to 43 squared and 44 squared minus 1. And it's even for everything else. So we fill in the gaps between these intervals. 2 squared to 3 squared minus 1, because you'll have the squares 1 squared and 2 squared up to them, and so on. So it goes up to 44 squared, and then we have to cap it at 2005. Now it's time to count. For how many n is S of n odd? Well, we just have to sum up how long these intervals are. The biggest interval at the end is 44 squared minus 43 squared. That's how many integers it contains. The interval after that, which isn't listed in the 5th bullet point, but it is included in our sum here, has 42 squared minus 41 squared. And so on, until the smallest interval has 2 squared minus 1 squared integers. And when is S of n even? Well, that happens. So let's first simplify this then. So 44 squared minus 43 squared is 87. It's 44 plus 43 by the difference of squares formula. 42 squared minus 41 squared is 83. The next one is 79, and it steps down by 4 each time. We have that chain. And if we want to find b, the number of n for which Sn is even, we're going to have to sum up the intervals here. Now the largest interval has only this many integers, because it doesn't end at a perfect square minus 1. So it's 2006 squared minus 44 squared. But the rest of it continues with the pattern. 43 squared minus 42 squared, then 41 squared minus 40 squared, and so on. And let's simplify that. So 2006 minus 44 squared is 70. If we remember that 44 squared is 1936. And the rest of them form an arithmetic sequence. So 43 squared minus 42 squared is 85, because it's 43 plus 42. The next one will be 81, and so on down to 5. So if you'll see here, we have a sum for A and a sum for B, and each they have the same number of terms. Each of these lines up, as you can verify. So when we take the difference B minus A, well, we can subtract the corresponding terms. 70 minus 87, then 85 minus 83, then 81 minus 79, down to 5 minus 3. So we have 70 minus 87 here, and all the rest of these terms are going to be 2, because they're in a staggered arithmetic sequence. And so we can get a final sum. 70 minus 87 is minus 17. And you can verify that there are 21 terms here for a sum of 42. And when we add it all up, it ends up being 25. So does anyone have any questions about this one? If not, then let's move on to another problem. And Aditya will be talking us through this.
So this is our next problem on divisors. So I'll give you a couple of minutes to think about it. So for this, let's first start by assuming a prime factorization for A. So we can just let A be P1 to the E1, P2 to the E2, all the way to Pi to the EI. So now if we look at A to the K and the number of positive divisors of this, can anyone say what condition there is on the number of positive divisors of A to the K? Yep, so it has to be 1 mod k, and the way you would see this is that A to the k has this prime factorization, and as Daniel told us already, we can find the number of positive divisors like this, and so it's k e1 plus 1 times k e2 plus 1 all the way to k e1 ei plus 1, and if we take this whole expression mod k, it's just 1 times 1 times 1 dot dot dot. So this happens to be 1 mod k. So the next question is this the only condition we need on n? As in, do all integers n that are 1 mod k satisfy this property? And if so, does anyone know of an example? Yep, so we can take 2 to the n minus 1 over k, so that a to the k is 2 to the n minus 1, which has n divisors. So this means that anything that is 1 mod k has the property that it is k nice, and that's the only condition we need. So we essentially want to count the number of positive integers less than 1,000 that are neither 1 mod 7 nor 1 mod 8. And we can just use principle of inclusion and exclusion for this. So first, the number of integers in this range that are 1 mod 7 is the ceiling of 999 over 7. And so this comes out to 143. And similarly, we can do the same thing for 8, so that there's 125 integers in this range that are 1 mod 8. And finally, so if we add these two, it tells us how many are 1 mod 7 or 1 mod 8, but we have to subtract the double count, which is when they are 1 mod 56. So we can find that there are 18 integers that are 1 mod 56. And then our final answer is 999 minus 143 minus 125 plus 18, because we started with all the 999 integers, and then we're subtracting the ones that are 1 mod 7, subtracting the ones that are 1 mod 8, and we have to add back the ones that are 1 mod 56 because they were counted twice already. So we already subtracted them twice. And once we add that back, we can get our answer of 749. So does anyone have any questions on this? Okay, great. So we'll move on to our next section, which is on multiplicative functions. So in number theory, one very useful property that some functions have is that they're multiplicative. And in this setting, it just means that if we take two integers m and n that are relatively prime, then f of m times f of n is equal to f of m times n. So so I guess one example that you might be familiar with is Euler's totient function. So in this case, we have that phi of mn is equal to phi of m times phi of n when GCD of m and n is 1. And you can verify this directly. One way to do it is just to use the formula for Euler's totient function. So the reason why knowing that a function is multiplicative is very useful is that sometimes when we want to evaluate a function at some value, we can separate it so that we only have to evaluate it at each of the prime powers, and then we can multiply all of the evaluations at each of the prime powers. And this is very helpful because we'll be evaluating it at a smaller value than before. So, and also primes are usually easier to work with. So this is like a very important property. So we'll discuss some applications in the next two problems. So our first problem is this one. So I'll give you a couple of minutes to think about it. Okay, so let's get started. So the first thing is, how do we even start by simplifying n to the n mod 2017? So does anyone have any ideas for this? Yeah, so one thing we can do is first take n mod 2017, but doesn't really help us. We can't really do this in the exponent. So is there anything else we can use to simplify the exponent, or at least reduce it to a smaller integer? Yeah, so if we look at Fermat's little theorem, we know that n to the 2016 has to be 1 mod 27, or yeah, 1 mod 2017. So that means if we just take n mod 2016 and reduce that, it's still going to have the same value as n to the n mod 2017. So let's just think about this more formally. So we can let x be n mod 2017 and y be n mod 2016. So now our expression can be simplified to, we can simplify it first to x to the n and then to x to the y mod 2017. So now we have the x to the y is 1 mod 2017. And another thing to note here is that the range that we were given is essentially 2017 times 2016 consecutive integers. Um, so, so if we look at the Chinese remainder theorem here, if we have that n is x mod 2017 and y mod 2016, from x and y, we can uniquely determine n. So, so now instead of counting the number of values of n, we can instead look at counting pairs of x and y. So now the next question is, how can we start counting the pairs x and y? Is there any property or result that we can use to simplify this further? So one thing here is that remember that 2017 is a prime. So maybe try to think back. A couple of lessons ago, we discussed something that we could use for prime numbers. Um, so here, one of the problems is that we don't know the order of x mod 2017. So it's hard to give a specific like how like you can't it's hard to give a specific um constraint on y from this. So is there something else that we can use to be able to get a constraint on y? Okay, so one thing we can do is use primitive roots. So we know that there does exist a primitive root g mod 2017. And the nice thing about primitive roots is that the order of g mod 2017 is 2016. So, and we can find some k such that g to the k is equal to x. So if we plug this in, we get g to the ky is 1 mod 2017. But since the order of g is 2016, that means that 2016 has to divide ky. And if we remove the common factor between k and 2016, that means that 2016 over the GCD of 2016 and k has to divide y. So does anyone have any questions up till this point? Okay, so as y ranges from 0 to 2015, the number of y that will satisfy that divisibility is essentially 2016 divided by 2016 over the GCD of 2016 and k, because we're looking at 2016 consecutive integers from 0 to 2015, and we can divide by the number that y has to be divisible by. So if we simplify this a bit, we just get that the number of y that satisfy this divisibility for a fixed k is the GCD of 2016 and k. And so remember before we were counting the pairs of x and y? Well, now we really can just count pairs of k and y, because we use the properties of a primitive root. So like k and x are essentially interchangeable. You can go to x by doing g to the k. So now we just have to count pairs of k and y. And as k goes from 1 to 2016, the number of values of y for each value of k is GCD of k in 2016. So if we add this all up, the number of pairs has to be the sum from k equals 1 to 2016 of GCD of k in 2016. So now to try to simplify this sum or evaluate it, let's first let f of n be the same sum, but we replace 2016 with n. So does anyone have any ideas for how we can evaluate this sum or any properties that it might have for this function f of n? Yep, so f is multiplicative. One way we can show this is actually just through direct multiplication. So we can just take a and b to be relatively prime and multiply f of a and f of b. So this is what we get for f of a and times f of b. And so we get this double sum with GCD of I and A times the GCD of J times B, J and B. So the key step in simplifying this sum is if we just let k be the unique integer such that k is I mod A and J mod B by the Chinese remainder theorem. And we can do this since A and B are relatively prime. So now the GCD of I and A has to be equal to the GCD of K and A. You can verify this with the Euclidean algorithm if you want. And similarly, the GCD of J and B is equal to the GCD of K and B. And now, instead of summing over I and J, since we have translated this into a unique integer K, we can just write this as a single sum over K. And this would go from 1 to AB. So if we do this, we get this sum from 1 to AB of GCD of K and A times GCD of K and B. But since A and B are relatively prime, GCD of K and A times the GCD of K and B is the GCD of K and AB. Yeah, so this is easy to verify since we know that A and B are relatively prime. So this means that f of A times f of B is equal to f of AB. So f is multiplicative. So how do we use this? Remember that I said that we could use this by trying to separate it into its prime powers. So here we have f of 2016. And so the 2016's prime factorization is 2 to the 5th times 3 squared times 7. So we can write this f of 2016 as f of 32 times f of 9 times f of 7. And now each of these terms is much easier to evaluate. For example, f of 32, we can find by noting that there are 16 odd integers, so 16 of them will have a GCD of 1. There are 8 integers that are divisible by 2 but not 4, and so on. We can just add up all of these terms, and we get 112. And similarly for 9, we get 6 times 1 plus 2 times 3 plus 1 times 9, which is 21. And for 7, we get 6 times 1 plus 1 times 7, which is 13. So our final answer is 112 times 21 times 13, which is 30,576. So does anyone have any questions on this? Okay, so we'll move on to our last problem of the day, and Brian will take over.
Okay, so here's the last question of the day. And so yeah, I'll give you guys a bit of time to think about it, and then we'll be going over it. Okay, so when we first see this question, like what are some things that we can try? Right, well, so first they give us this condition that like f of 1 is greater than 0. Right, so we want to somehow be like use that at some point. So what if we just like plugged in n equals 1? And what this gives us is f of 1 squared is equal to 1, and since it's positive, f of 1 has to equal 1. Right, so now that's that, and now we claim that this is like enough to basically just identify all of the other values of f. Right, so, well, the first thing that we'll do is that we claim that f is multiplicative. Hold on. So we claim that f is multiplicative. So we recall the definition of multiplicative, and so we basically want to show that. Right, so, well, how would we do that? Well, basically, we have this nice thing that basically, if you look at it, if you plug in n equals a, for example, then it can basically just tell you what f of a is in terms of a bunch of previous terms, right? So, well, so that motivates us to plug in n equals a, n equals b, and n equals ab. But first, we look at the divisors of a and b, right? Because we know that if we're going to be plugging stuff in, then we care about their divisors. But basically, so if we look at the divisors of AB, well, every divisor has some primes that come from A and some primes that come from B, and these primes are mutually exclusive because A and B are relatively prime. Right, so what this tells us is basically there's a unique way to write it as a product of a divisor of A and a divisor of B. And this is very useful, right? Because basically, what this allows us to do is, well, if our equation tells us that we can express things in terms of smaller terms, right? So we're going to try to use induction. And basically what happens now is if we plug in the things that we set out to plug in, then basically like f of d1 and f of d2 will combine to equal to into f of d1 d2, and f of a over d1 and f of b over d2 will combine into f of ab over d1 d2, with the exceptions of when d1 equals 1 or when d1 equals 1 or a and d2 equals 1 or b, because we have not shown whether f of a, f of b equals f of ab yet, right? So that's basically what that term at the end corrects for. But we know that by induction, everything else is the same, right? So this is very effective because basically we also know that 1, so 1 is equal to 1 times 1, but also when we plug in n equals ab, it just gives us the thing that we had without the error term, right? Which basically tells us that this error term is 0, which basically says that f of ab does actually equal f of a, f of b, right? So, well, now what? Well, now basically we want to see the behavior along powers of primes, right? So, well, the first thing we note that is that it doesn't actually matter what the prime is, because like basically it's uniquely determined by f of x divisors. And then if we induct upwards from like k equals 0, where they're all equal to f of 1, then basically you can see that all of them should be the same, like independent of p. Okay. So now from here, what we can do is basically we just try to find f of p to the k. So let's just call it ak. And so, well, a technique that you can do to analyze a sequence is like you can write it as a generating function, right? And so what motivates us to do this in this situation in particular is because if you look at the original equation basically just tells you a0 ak plus a1 ak minus 1 plus a2 ak minus 2 plus all the way up to plus ak a0 equals 1 for all k, right? And so basically if you look at it in this way, you're basically, if you think about squaring the generating function, well, then you get exactly the terms that you have on the left-hand side. And then on the right-hand side, your identity tells you that it has to equal 1, which tells you that it's equal to 1 plus x squared plus all the way up to infinity, which is 1 over 1 minus x. Okay, so now we want to, now we see that g of x equals 1 minus x to the negative 1/2. And we take the positive square root because we know that a0 is positive 1. Okay, so well, now we just have to find the coefficients of this. And this can be done with the extended binomial theorem. So basically, like if you think about what happens with the coefficients of like 1 minus x to other powers, then you basically just use the binomial theorem again, like except instead of taking integers, choosing integers, you have negative 1/2 choose integers, right? And basically you can think about it as like negative 1/2 times negative 3/2 times negative 5/2 all the way down to negative 1/2 minus n minus 1 all over n factorial. And then basically if you rewrite it, you can see that it's equal to negative 1 to the n times 2n choose n all over 4 to the n. Right. And so now we remember what we're looking for. We're looking for we're looking for 2018 to the 2019 f of that. And well, we split it into its prime divisors. And then we can calculate f of each of those terms as a 2019. And then so it's just a 2019 squared, which is the thing in the box. Does anyone have any questions about it? If not, I guess that's the last problem of the week. So yeah, that concludes class for today.
Thank you to everyone for attending. I guess we'll pick up with this topic again next week.